Valve types and application mapping. Choosing the right valve geometry. This module is where control valve theory turns into engineering judgment. By now, you know how valves behave and how they're built. The real design skill lies in mapping valve geometry to process reality. Pressure drop, rangeability, maintenance philosophy, economics, and long-term operability. There is no best valve, only the right valve for a given service. Globe control valves image. Strengths in precision throttling. Globe control valves are the benchmark for accurate, stable, repeatable throttling. Their linear stem motion, guided trim, and predictable flow geometry make them exceptionally controllable. Key strengths: high resolution at small signal changes, stable plug guidance under varying differential pressure, predictable inherent characteristics, excellent shutoff performance. From a control perspective, globe valves translate controller output into smooth, proportional flow change, which is why they dominate demanding control applications. Pressure drop behavior. Globe valves inherently create high pressure loss due to their tortuous flow path. Design implications: ideal when large pressure drop is available and desirable. Unsuitable where pressure recovery must be maximized. Perform well in flashing, cavitating, or choking services when properly trimmed. In many processes, the valve is intentionally used as the primary energy dissipation device, and globe valves excel in this role. Balanced versus unbalanced trim. Unbalanced trim, simpler construction, excellent shutoff tightness, high actuator force required. Practical for smaller sizes and moderate delta P. Balanced trim. Pressure forces partially cancel. Smaller actuator size, improved stability at high delta P, slightly reduced shutoff capability. Trim balancing is a mechanical decision with control consequences. Poor balance selection leads to actuator saturation, hunting, or premature wear. Typical applications: globe valves are preferred when tight control is mandatory, pressure drops are high, noise and cavitation must be managed, process variability must be minimized. Common services: steam pressure and temperature control, feed water and boiler control, reactor feed control, high pressure gas throttling. Rotary control valves. Image rotary valves trade some inherent precision for capacity, speed, and compactness. When applied correctly, they outperform globe valves in many modern plants. Butterfly valves, standard versus high performance. Standard butterfly valves, high flow capacity, lightweight and economical, nonlinear control near closed position, limited throttling precision. High performance butterfly valves, offset shaft and advanced seat designs, improved control range, better shutoff and durability, suitable for moderate control duties. Butterfly valves dominate large diameter services where globe valves become impractical. V-notch ball valves. V-notch ball valves significantly improve throttling performance over conventional ball valves. Key characteristics: enhanced rangeability, better low flow resolution, high capacity at full open, excellent for dirty or fibrous services. They are a strong alternative where space is limited, moderate precision is acceptable, high flow rates are required. Eccentric disc and eccentric plug valves. These valves bridge the gap between globes and rotary designs. Eccentric disc valves, reduced seat wear, improved throttling stability, high flow capacity. Eccentric plug valves, rotary motion with plug-style throttling, better control than butterfly, more tolerant of solids and fouling. They are often selected where fluids are dirty or erosive, maintenance access is limited, moderate to good control quality is required. Rangeability and torque considerations. Rotary valves introduce torque-based design constraints. Key factors: torque increases nonlinearly with pressure and flow. Actuator sizing must consider worst-case dynamic torque. Seat wear changes torque over time. High rangeability often conflicts with compact actuator sizing. Underestimating torque is one of the most common rotary valve design failures. Comparative selection logic. When not to use a globe valve. Despite their precision, globe valves are a poor choice when line sizes are very large, pressure drop must be minimized, weight and footprint are constrained, budget limitations dominate the design, process fluid is highly dirty or fibrous. Using a globe valve in these cases often results in over-designed, underperforming systems. When rotary valves outperform globes. Rotary valves are superior when large flow rates are required, pressure recovery must be high, Fast response is beneficial. Installation space is limited. Cost per diameter is critical. Modern high-performance rotary designs have narrowed the precision gap significantly, making them the preferred solution in many applications. Cost versus performance versus maintenance trade-offs. Valve selection is always a three-way compromise. Performance: control accuracy, stability, noise, cavitation resistance. Cost: initial purchase, actuator size, installation. Maintenance: wear rate, accessibility, trim replacement frequency. A low-cost valve with high maintenance often becomes the most expensive option over its life cycle. Conversely, overspecifying precision where it is not required wastes capital without improving control. Module 3 is about engineering maturity. Once you can justify why a specific valve geometry belongs in a specific service, and just as importantly, why others do not, you've moved from catalog selection to true process control design. Flow characteristics and control behavior. How valve geometry translates into control quality. If valve type selection answers what hardware to use, flow characteristics answer how that hardware behaves once it is in the loop. This module is where many control problems are quietly designed into a system, often unintentionally. A valve's flow characteristic is not just a curve in a catalog. It is a gain-shaping mechanism that determines stability, sensitivity, and achievable control accuracy across the operating range. Inherent flow characteristics. Image. The inherent flow characteristic describes the relationship between valve travel and flow rate at constant differential pressure across the valve. It is a pure geometric and trim design property, independent of the process. Linear. A linear valve produces equal changes in flow for equal changes in valve travel. Engineering implications: constant valve gain across stroke, predictable behavior in laboratory conditions, simple to understand but rarely optimal in real processes. Where linear works: systems with relatively constant pressure drop, some level and flow applications with stable hydraulics. Limitation: in real plants, pressure drop is rarely constant, causing installed behavior to deviate significantly from linearity. Equal percentage: an equal percentage valve changes flow by a constant percentage of the current flow for equal increments of travel. Engineering implications: valve gain increases with opening, low sensitivity near closed position, high capacity near full open AS. This characteristic naturally compensates for changing system pressure drops, making it inherently adaptive to real process behavior. Quick opening. A quick opening valve produces large flow changes at small openings. Engineering implications: extremely high initial gain, poor throttling precision, minimal resolution near closed position. Typical usage: on-off or sequencing services, safety and relief-related applications. Quick opening is rarely appropriate for modulating control loops. Installed characteristics. Image. The installed characteristic is the relationship between valve travel and flow once the valve is installed in the actual piping system. This is what the controller truly sees. Effective piping, pressure losses, and system curves. In a real system, total pressure drop is shared between the valve and the piping. As flow increases, piping losses increase non-linearly. The valve no longer experiences constant delta P. Result: linear inherent valves become quick opening when installed. Equal percentage valves become nearly linear. Valve gain changes with operating point. This interaction is why control valves cannot be selected in isolation from the process hydraulics. Why equal percentage dominates industrial control. Equal percentage valves dominate not because they are theoretically superior, but because they are practically forgiving. Key reasons: they accommodate wide operating ranges. They linearize naturally when installed. They maintain controllability at low and high loads. They reduce gain-induced instability across throughput changes. In most flow, pressure, and temperature loops, equal percentage characteristics provide the widest usable control window. Mismatch between inherent and installed behavior. A common design failure is selecting a valve characteristic based solely on inherent curves. Consequences of mismatch: excessive loop gain at low flow, poor resolution at normal operating point, oscillations during load changes, frequent retuning across operating regimes. Design engineers must always think in installed behavior, not catalog behavior. Rangeability and turn-down image rangeability defines how much usable control a valve can provide, from minimum controllable flow to maximum rated flow. What limits usable control range? True control range is limited by more than trim geometry. Key limiting factors: seat leakage at low openings, stem friction and stiction, actuator resolution, positioner sensitivity, process noise relative to signal. A valve may physically pass flow at low openings but still be uncontrollable due to poor repeatability. Seat leakage versus control precision, tight shutoff and fine control are often competing objectives. Engineering trade-off: tighter seats improve isolation, softer seats increase friction and hysteresis, metal seats improve stability but allow leakage. For modulating control, small predictable leakage is often acceptable, unpredictable movement is not, but designing for zero leakage at the expense of controllability frequently degrades loop performance. Practical rangeability versus catalog values. Catalog rangeability values assume ideal actuator, zero friction, perfect position feedback, clean, steady process conditions. In reality, practical rangeability is often 30 to 50% of catalog claims. Process variability consumes usable resolution, wear reduces effective range over time. Experienced engineers select valves based on achievable rangeability, not theoretical limits. Flow characteristics are not an academic detail. They define how a valve feels to the controller. When geometry, inherent behavior, and system dynamics are aligned, the valve disappears into the background and control feels effortless. When they are not, no amount of tuning can compensate. This is why understanding flow characteristics is central to real-world control quality.